Hi, welcome to the notes for H3-1. Today we're going to review the properties of exponents. So exponents is something that a lot of us will find challenging. We've been doing them probably each year since middle school. So I want to make sure that we feel better about them. So we're going to take our time and review some of these properties as we start out chapter 3. So starting out with the first property, we have a to the power of m times a to the power of n is equal to a to the power of mn. So what we're looking at here is we're multiplying some number, it's the same number, right, times itself there, but it has different exponents. So when we multiply two numbers of that same base there, all we're going to do is add those exponents together, right? Just a shorter way of writing it. If we want to expand out our first example, x squared times x to the seventh, right? X squared really means x times x. We know x to the seventh means x times itself 7 times. So when you think about that expression, we can say the thing that's really happening here is we're multiplying x times itself 9 times. So this is the same thing as saying x to the power of 2 plus 7, which gives us x to the 9th power. That would be our answer for that example. Okay, now, because we're in Algebra 2, we're going to start to see some things that may look a little different. Instead of having just numerical exponents, you're going to see some that have variables up there. So the next example, we have 3 to the power of x times 3 to the power of y. Well, since we're multiplying two numbers at the same base, we know our answer is going to be 3 raised to the power of however many x's plus however many y we have there, right? So we're going to add those together. Our expression would be 3 raised to the power of x plus y. All right, and as we go down to the bottom, you'll see we have t raised to the power of x times t raised to the power of x plus 5 times t raised to the power of x minus 5. So now we've got three terms that are being multiplied, right? But they're all t's, in which case we can take it and apply this rule the same way. We can say this is going to be t to the power of this exponent plus this exponent, so plus an x plus 5, plus this exponent, which would be like a plus x minus 5, right? So everybody can see where those exponents are coming from. And then we'll just take it and we'll simplify our expression that's up here in the exponent, right? So what we have here will end up being t raised to the power of, well, we've got an x plus another x, right? So in the end, we'll have 3 x's. And then we've got a 5 plus a negative 5. That's going to end up canceling out and giving us 0. So our answer ends up being t raised to the power of 3x. Let's move on. So a second property is when we have a product raised to a power, right? If I have a times b and I'm raising that entire product to the power of m, that simply means that each of the factors is going to be raised to that power of m. Okay, so you could think about this as, you're going to multiply a times b times itself however many times. So the first one, we have 2a, and it's raised to the second power. Okay, remember, this really just means we're going to do a 2 times an a, right? Because that's what that means right here. It's 2 times a, and we're going to multiply it times another 2 times a. And if you wanted to do it the long way, you could do that and then expand it out, and we could reorder everything using the commutative property and do 2 times a, which would simplify to, right, we've got 4 times a squared, or 4a squared. Okay, or a second way to do it there is to take it and think about applying the exponent to each of the factors, right? So we could think of this as 2 to the second power times a to the second power, which gets us the same thing, 4a squared. Not everyone is going to see it the same way, so the important thing to recognize is how do you see it, and hopefully we can just be consistent and use whichever method that you see it. So let's look at the next one. We have a product of, it says the opposite of a times b to the fourth. Or we could think of this as being a -1 times an a times a b to the fourth, and you're multiplying that times another -1 times a times b to the fourth. And the reason I put parentheses around that, right, is I don't want it to look like subtraction because I'm multiplying another -1, okay? But when we're trying to use the exponent rules, we could think of this as, well, we're going to be multiplying -1 times itself twice, times a times itself twice, times b to the fourth times itself twice. So as we look to simplify each of those, right, we know here that -1 times -1 is going to give us a +1. We can just go ahead and write the 1 out there, that's fine. We know that a times a is going to give us an a squared. And then when I do b to the fourth times b to the fourth, right, that means b to the fourth times b to the fourth would really be just like our last rule that we just did. We have b times itself 4 times b times itself 4 times. Really, we're multiplying b times itself 8 times. So then we'll take it and we'll just finish simplifying, right? We don't need to include the 1 out there now, so we'll have just an a squared b to the 8th power. And that would be our answer. Okay, so let's jump into this next part here. And this one kind of overlaps what we just did a little bit. I know that some of us may know some other ways to deal with this b to the fourth to the 2nd power, and that's what we'll kind of look at here in this next one. When I have a term that's being raised to a power already, and then we raise it to another power, right? That means that we're going to end up taking these two exponent values and we're going to multiply them. Okay, so our example here, we have -3x squared y z to the 3rd, and it's being raised to the 3rd power. Okay, so when we look at it, how many factors are in here? We've got a -3, an x squared, a y, and a z, right? So there's 4 different bases there, and each of those bases is going to be raised to the 3rd power. Okay, so we could take it and expand it like we did on some of those first ones, but like these are getting longer and longer, so we're going to have more and more expansion, and that just takes longer. So we'll try to use the shortcut. So the first thing here, right, we're going to take -3 and we're going to raise it to the 3rd power. Then we're going to take x squared, right, I'm putting parentheses around it, and then I'm raising it to the 3rd power. Then we're going to take our y, raise it to the 3rd power. And last but not least, we're going to take that z, it's already being raised to the 3rd power, and then we're raising that to the 3rd power. So let's take this and simplify this down now. First, we'll look at -3 to the 3rd. We know that's -3 times -3 times -3. And when we have an odd number of negatives, we know that that answer is still going to end up being negative. And 3 times 3 times 3 is 27. Okay, now when we do x squared to the 3rd power, let's just kind of illustrate why this rule occurs the way it does. This is saying x squared times x squared times x squared, right? Or really x times x times x times x times x times x. How many times are we really multiplying x times itself, right? That would be 6 times. Well, we get that by just doing our 2 times our 3. So when we raise a power to a power, we can multiply those, and we should end up with x to the 6th power, right? 2 times 3 gives us 6. On to the next one here, you'll see we have that y to the 3rd power. Well, y, remember, is raised to the 1st power right now. So when we take this and we do 1 times 3, that's going to give us 3. So we're going to have times a y to the 3rd power. And then last but not least, when we do the z to the 3rd, again raised to the 3rd power, it's like z to the 3rd times z to the 3rd times z to the 3rd. Well, we can take this and multiply these. 3 times 3 we know is 9. So we have z to the 9th power. Okay, so let's just take this and put this all together. We've got negative 27, x to the 6th, y to the 3rd, z to the 9th power. All right, down below, we've got an a raised to the power of x minus 4 times an a raised to the power of x plus 2, and then that's being squared. So we're going to have to kind of look at our order of operations or look at what's happening here. Right, so we have this a, it's being raised to the power of x minus 4 times an a raised to the power of x plus 2. And then remember, this exponent simply means we're multiplying that times itself again, right? So there's actually 3 bases here. They're all a, which means you could take this and just add all the exponents together. Or if we're trying to practice this rule, right, so or this exponent property, we could think of this part right here, right? If I'm taking this power and I'm raising it to the 2nd power, we're going to end up multiplying. So we're going to distribute this 2 through. So this is going to give us the same thing as saying a to the power of x minus 4 times a, and then when I multiply my 2 through, right, 2 times x is going to be 2x, and 2 times 2 is going to be 4, so we have plus 4. And so this right here, what we see, is the same as this. It's just we've already combined one pair. So let's just go ahead now and apply that property we've already talked about, right? Multiplying 2 numbers at the same base, we're going to add the exponents. So we'll say x minus 4 plus a 2x plus 4. And I don't really need grouping symbols because we're adding. So then we'll just go ahead and combine our like terms. We've got an x and then 2 x's. So we'll add those together to get 3x. So a to the power of 3x. And then we've got a negative 4 plus a positive 4. So those are going to cancel out. So we're left with just a to the power of 3x. If you're having questions, please make sure you mark them down. If you're doing this outside of class or I'm not there, you can save those questions and I'll gladly answer them when I return. Let's look at the next part. So now, how does the distributive property come into play with these exponent rules? Well, you see some different expressions here. Okay, the first one says we're doing x times the quantity of x to the 3rd plus 3x plus 2. Right, so we know that we would end up distributing our x through this quantity. So when I do x times x to the 3rd, right, and you do this quite a bit, you probably don't even think about it, but x times x to the 3rd, we're really adding the exponents, right? So x to the 1st times x to the 3rd gives us x to the 4th. Okay, now when I do x times the 3x, right, it's like 3 times x, which simplifies to 3x squared. And then if we have no x's on our 2, it would end up being plus 2 times our x, which is like x to the 1st. And that's our answer. At any point, please feel free to pause the video and try it yourself, and then you can check to see if you get them correct. We'll start out here. We've got a squared b to the 3rd, and we're multiplying this times a b to the 4th first. So our first expression, we've got a squared b to the 3rd times a b to the 4th, right? And then we're going to have a minus, right, because we're going to multiply this whole thing times this. So minus 3, right, because this is like a 1 times a 3 gives us 3. I've got an a squared times an a, and then I'm just going to put my b to the 3rd afterward, right, because we can rearrange them because it's multiplication. It follows the commutative property. And now we'll just go ahead here and combine, right? We have this term, we have this term. We're just simplifying those. Excuse me. So a squared b to the 3rd times b to the 4th is going to be b to the 7th, because 3 plus 4 is 7. We have minus 3, a squared times a is a to the 3rd, and then we'd have b to the 3rd. Okay, and since our expressions here don't have the same the same exponents on the variables, they're not like terms, and that's as far as we can go. This would be our answer. Okay, Next one looks really hard and confusing, but really it's the same thing that we have already done. Think about what you did up here in this, right? We just distribute this x through, excuse me, and we just added the exponents, right? So I have an x, I have an x, I have an x, and an x, right? Which means that when I distribute this through, I'm going to be able to add the exponents on all of these. So the first one, when I do an x raised to the power of h plus k times an x raised to the power of 2h minus k, I'm going to have an x to the power of h plus k plus this 2h minus k. Okay, and then after I've multiplied that, we'll simplify it in a moment. We're going to multiply it times this one. So, right, we're going to have a negative in between. And since it's the same base again, we're going to have just the x. And we'll have our h plus k, right, our original part up here, plus our h minus 2k. Right, so we're adding all that there. Right, I'll think of it in pieces, so hopefully you can see it. And then we're going to multiply this one times our last term here, which is going to be plus x. And we had an h plus k to start, and now we're adding just this k at the end, so plus another k. And now we just need to take it and simplify our exponents. So our first one will be x. And then when I do h plus 2h, I'm going to have 3h. And then k plus a negative k is going to cancel out there. So we have just an x to the power of 3h minus x here. And now we need to combine in here. We have an h plus another h would be 2 h's. And then we have a k plus a negative 2k, which is going to end up giving us a negative k. So we'll say minus k. Oops, I don't know why I wrote minus 2k. I meant minus k. And then our last one will have plus. We've got an x, and I've got just a single h, and then it looks like I've got 2 k's, so plus 2k. And then we can look at this. None of these are exactly the same in terms of the exponents, so we can't really combine anything together, right? Since our exponents are different and we're adding between here, we can't combine them at all. And this actually ends up being our answer. All right, let's move on. So this is just a quick review on zero exponents. Remember, anything raised to the power of 0, except for 0, any non-zero number raised to the power of 0 is always going to equal 1, right? So you see here, a to the power of 0 really equals 1, as long as a doesn't equal 0. It doesn't matter if there's a product in there, right? A times b, as long as neither a or b is equal to 0, right? This will end up equaling 1. So we'd say here, right, a cannot equal 0. A and b, neither of those can equal 0. And then on our last one here, right, we're just going to assume a and b don't equal 0. Even if it's like a fraction or something really ugly inside of here, it doesn't matter. If the whole thing is raised to the power of 0, the whole thing equals 1 still. Okay, so anything raised, any non-zero number raised to the power of 0 is always going to equal 1. All right, so last little bit here, we're just going to look at solving some exponential equations. Okay, looking at the same base. We've seen some of these in the homework in the last chapter. So we're just going to focus on just some of the basics again. So number 1, we have 3 to the power of 2x minus 1 is equal to 3 to the power of x plus 4. Well, if these things are both really equal, right, if 3 really equals 3, if I raise 1 to a power, right, the exponent here, this power, is going to have to be the same on both of them in order for this to be true. So all we're going to do then is we're just going to take the exponent, and we're going to set it equal to the exponent on the other side, right, because they already have the same base. If they have the same base, we can do that. That's what we're comparing, and then just solve that equation. right? So we're going to end up on this one with x is going to equal 5. And if we substitute it back in, you'll see we have 3 to the power of 2 times 5 minus 1 should equal 3 to the power of 5 plus 4. Well, 2 times 5 is 10, minus 1 is 9, so this is 3 to the 9th power should equal 3 to the 9th power. So we know that it's correct. But our answer here was 5. For number 2, we have 5 to the power of 4 minus x equals 25 to the power of x minus 1. Okay, so when we look at this one, our bases are not the same. So we need to make the bases the same. Okay, now, this is where I sometimes see some mistakes. We can't take 5 and suddenly turn it into 25. But we can take 25 and rewrite it as 5, right? So if I have 5 to the power of 4 minus x, right, that's the same thing as 5 squared raised to the power of x minus 1, right, if we're comparing it to this expression up here. Okay, so we've turned this 25 into 5 squared. Now they have the same base, and we can apply our exponent rules. So we've got 5 squared raised to the power of x minus 1. Remember, we have to multiply. So this is the same thing as 5 to the power of 2 times x minus 1, right? Is still equal to our 5 to the power of 4 minus x. So let's just take it now and set the two exponents equal. Once our bases are the same, what matters now is the exponents. So we'll take it and say 4 minus x is going to equal 2 times the quantity of x minus 1. And we can go ahead and simplify this by distributing it. So we have 2x minus 2 should equal 4 minus x. So you go ahead and solve it. And it looks like we've got 6 is equal to 3x. And then when we divide each side by 3, we will get that 2 is equal to x. So that looks like our answer. It's really easy to take it and plug it in and check it. Right, so up above, I've got 5 to the power of 4 minus 2 should equal 25 raised to the power of 2 minus 1. Well, 5 to the power of 4 minus 2 is 5 squared, which is 25. And then 25 to the power of 2 minus 1 is 25 to the first power, and you see that it works out. So really easy to check these. I would expect that you are checking them. All right, 2 more here and we're finished. So number 3 says 8 to the power of x equals 1/4. So look at these numbers and think about what number could we rewrite them as. Okay, so we know that when we focus on the 8, and I'm going to focus on this 4, right? Both of those can be rewritten as base 2. This is 2 to the 3rd power raised to the power of x. And 1/4, right? 4 is the same thing as 2 squared. So right now I'm going to look at it as 1 over 2 squared. Okay, but I don't want to have it down in the denominator. So think about what happens when we move it up to the top, right? It becomes 2 to the negative 2nd power. That's something we've seen before, and don't worry, we'll review that more as we move forward. Okay, and then think about applying your exponent property here, right? 2 to the 3rd to the power of x would be 2 to the power of 3x. And now that our bases are the same, right, we are just going to use our exponents here to solve. We're going to say 3x is equal to negative 2. We'll divide each side by 3. And x is going to equal negative 2/3. And if we took that and we plugged it in, right, we don't have anything to plug in on the right side. We'd have just an 8 raised to the negative 2/3 power, right? We're saying that's supposed to equal 1/4. Okay, so, and if you forgot how to do this, that's okay. We're going to review this. But if you do remember here, right, this is the same thing as saying like 8, right? We're going to do let's do it like this. We'll do 8 to the 2/3 power, and then we'll just go ahead and worry about the negative here in a second. So remember, 2/3, right? We're talking about power over root, right? So it's power over root. So we're going to do the second power, and we're going to do the third root or the cube root. So I'm going to do the cube root of 8 squared, and then we'll raise it to the negative first after that. So cube root of 8 is 2, 2 squared is 4, and then if we have 4 to the negative first, right, that's going to be 1/4. So we know we're correct. I'm totally fine with you checking that one on the calculator here until we review those properties. All right, let's do the last one. We have 7 times 49 raised to the power of negative 3x minus 2 is equal to 7 to the power of x plus 2. So we've got 3 bases right now. Right, this is like 7 to the first. We have 49, which we're probably going to have to rewrite that one, right? Because we need it to be a 7 also. So this is really 7 squared raised to the power of negative 3x minus 2. Okay, we've still got our 7 times that. Okay, and then I'll just copy this other part down. We haven't touched the right side yet. So ask yourself, what property do we want to apply first? Well, we've got a power to a power. So let's go ahead and apply that. This would be 7 to the power of 2 times negative 3x minus 2. We're going to distribute that through. Excuse me. 7 to the negative 6x minus 4th power. And I'm sorry, my pen is starting to struggle here. It must be getting low on battery. And then I'm just bringing everything else down. Okay, now we still need to focus on this side, right? We need to simplify. Well, if I've got 2 numbers at the same base and I'm multiplying, what do I do with the exponents? Think back about your properties, right? We're going to add them together. So this is just going to be 7 to the power of negative 6x minus 4, and then we're adding 1 to that. Like I said, I'm sorry, I don't know why it's not writing here. Hopefully we can make it to the end. Right, and this is supposed to equal 7 to the power of x plus 2. So what I would do here then is we have the same base. So let's just go ahead and compare the exponents. So as we do this, let's just go ahead and combine this one, right? Let's simplify that. Negative 6x minus 4 plus 1 would be negative 6x minus 3 is going to equal x plus 2. And we'll go ahead here. Let's subtract x, add 3, add 3. I'm sorry, this is not writing very well at all anymore, but we'll make it. So negative 7x is equal to 5, and then we'll divide each side by negative 7. And it looks like our answer is going to be x equals negative 5/7. Okay, and with that, you can check it with the calculator if you want to, or just take my word for it. That should be it. This is the end of that section. If you have additional questions, please make sure you reach out or ask me in class when you see me. Thanks for watching.